Neural networks derive their power from being a highly general model whose parameters can be optimized to fulfill a particular task. However, one prominent challenge was exactly how to get those parameters optimized given some target and input data. One answer that has proved highly influential is backpropagation, proposed by David Rumelhart, Jeff Hinton, and Ronald Williams in 1986. Now, before exploring that method, let's touch briefly on neural network architecture. A feed-forward neural network generally consists of a set of n layers, each one feeding inputs into the next. Here is a schematic of the simplest kind of neural network, a multi-layer perceptron, where each neuron in one layer is connected to every neuron in the next layer. Now, when a neuron receives inputs from the previous layer, it calculates a weighted sum of them, plus some bias term. The result is then passed through an activation function, which can be any function in theory, to produce the output. Hence, the full formula is this, where x hat just represents the pre-activation output. Now, here are some commonly used activation functions. The linear activation just leaves x hat untouched, while the ReLU, or rectified linear unit, activation converts negative values to 0, and the sigmoid activation reduces inputs to the 0 to 1 range using this particular formula. Now, while the architecture of the network is typically fixed during training, these interlayer weights, omega, are allowed to change. And it is the weight configuration that specifies the task for which the network is suited. So the process of neural network training is the process of optimizing these weights via the use of a loss function and an optimization algorithm. Now, when an input is received by a multilayer perceptron as a whole, it produces an output vector y at each layer from 1 to n, with a loss function that typically, though not always, is applied on the outputs of the final layer. And this loss function is just a metric that defines the penalty given to the model during training. Now, since the loss value depends directly only on the final layer outputs, it depends on the rest of the weights of the network only indirectly. And if we can calculate the gradient of the loss with respect to each of these weights in the network, we would know how to shift these weight values in order to reduce loss. The idea here is that even though those other weights do not affect the loss function directly, they do affect it in the sense that they affect the output vector y at the final layer. Now, this whole process is called gradient descent. We calculate the partial derivative of the loss with respect to every individual weight in the network represented by this weight vector w. And then we push the weights in the opposite direction of this gradient using a step that's just scaled by the learning rate here. But don't worry about that now. Now, the overall goal is to find a global minimum of loss, or, barring this, at least a local minimum that is not much worse than the global minimum. However, at times we can certainly find ourselves stuck in positions where good minima are impossible to reach, given the existence of barriers in the loss landscape. But that problem is mitigated by allowing the model to traverse a high-dimensional weight space, in other words, to contain a very large number of weights in the network. The authors of the original paper in fact pointed out that high-dimensional weight spaces tend to provide opportunities to overcome barriers that would otherwise hobble training in lower-dimensional spaces. To take an example, imagine that instead of just omega 1, we now have a second weight called omega 2. Now, it might be that in this two-dimensional rather than one-dimensional weight space, some sort of path exists that would allow the model to travel to the global minimum without having to traverse a barrier. So, this is the general scheme, but the question remains, how do we derive the partial derivative of the loss with respect to each weight in the network? This method of gradient descent only works if all the weights are changed in tandem, or else all the benefits of having a very large weight space are not felt. So how exactly do we derive the directions in which these weights have to be changed. Well, that brings us to backpropagation. Suppose we're trying to calculate the gradient assigned to the weight between one neuron in the penultimate layer, neuron I, and one neuron in the final layer, neuron J. The first step in this procedure is to calculate the gradient of loss with respect to the output of neuron J. This would just depend on the form of the loss function, so it is easily calculable. Then, we work out the gradient with respect to the pre-activated output of neuron J. This can be just done via the chain rule of differentiation, where we know dl by dyj from step 1. Now, dyj over dx hat j just depends on the activation function being used. And for now, let's just use sigmoid as an example. In this case, differentiating with respect to x hat j is straightforward, and it gives us this expression here. So now the next step is to calculate dl over d omega ij, which is what we want. And again, this can be done using the chain rule. In this expression, dx hat j over d omega ij simply just evaluates to evaluates to yi, since the contribution of omega ij to x hat j is scaled by yi. And here we can also use the expression for dl over dx hat j that we derived in step 2. So now we have an expression for the gradient of loss with respect to the weight of interest using values of variables that are readily available. Now we know that this process can be done for every neuron in the nth or final layer. If we have dl over dy, we can calculate dl over d omega. But what about the other layers in the network? Well, the really great thing about backpropagation is that we can also calculate dl by dy for layer n-1, given that we know the value for layer n. And so, of course, from this, we can then find the value of dl over d omega as well for layer n-1. And if we do this iteratively, we could then find dl by d omega for any layer m in the network. And in this whole process, we can see that this step highlighted here is crucial. But how is it actually done? Well, say we have a neuron I, which is connected to every neuron k in the following layer. Then dl over dyi, where dyi is just the output of neuron I, equals the sum of this chain rule expression over every target neuron k. And remember that we can evaluate dx hat k by dyi as omega ik. And from our previous working, we can also express dl by dx hat k using this expression here. Hence, we can calculate dl over dyi just by using 3 variables. One is dl over dyk, where dyk is the output of the neurons of the next layer. And then dyk by dx hat k, which just depends on the activation function. And then omega ik, which is just the weight, which is already known. Hence, it is very feasible to calculate dl by dy for the previous layer. So in general, if we have a neuron P and neurons in the next layer represented by Q, and we want to find the weight, how the weight PQ should change, this entire backpropagation algorithm can be considered as powered by these 2 equations. Equation 1 allows us to calculate dl by dy for neuron P, given dl by dy for every neuron Q in the next layer. Equation 2 then allows us to calculate the gradient of L with respect to the weight between neuron P and one specific neuron Q, given dl by dyq. So, equation 1 is responsible for this horizontal motion here, backpropagating all the way to layer 1 from layer n, and equation 2 is responsible for translating dl by dy to dl by d omega for each neuron. Hence, this procedure is named the backward propagation of errors, or backpropagation for short. And this way, every weight can be adjusted simultaneously such that the network as a whole goes down the loss gradient. And this can be done through several optimization procedures, or optimizers, but that's a subject for another video. For now, thanks for watching.